Welcome. Today we are going to finish our discussion on reviewing gas laws. We're going to focus today on a concept that we call Graham's Law. It helps us to understand some basic words that you've probably heard before, but they're the terms diffusion and effusion. It will help us to understand how gases move, but it will also, as we're moving forward, it will use it as we understand the idea that while we talk about gases being ideal, that generally speaking, you should probably know that gases are not ideal, right? That generally speaking, when we talk about gases, that when they really move, that they move in a non-ideal fashion, which means that there actually is some issues with them losing energy. There is some issues with them being slowed down for various reasons, and that's what we're going to take a look at today, is understanding really how gases behave in nature. So with it in mind, if you haven't already done so, I'm going to ask you to take about 5 minutes right now. Pause the video. I have a starter question that I've posed to you. Now this question is a multiple choice question, but I would like you to write a sentence or two in which you explain why. So if you would, write this question down, select the best response, and then tell me why that would be. So it says a sealed container holds equal amounts of hydrogen and oxygen, and then it's opened, right? After 5 minutes, which of the below statements is most likely correct and why? So a sealed container holding equal amounts of hydrogen and oxygen is opened. After 5 minutes, which of the below statements is most likely correct and why? Again, if you need to pause the video to write this down, answer the question, and also explain to me why. In about 5 minutes, restart the video, and I'll go through the discussion. Again, this was a multiple choice question asking you to consider the information. What do you think would be most likely correct and why? So it says a container that held equal amounts of gas, it was sealed, and now it's open. After 5 minutes, which of the below statements is most likely correct and why? First of all, it says both gases will have effused from the container. Second one, more hydrogen will have effused. Third, more oxygen will effuse. Fourth, neither the hydrogen or oxygen will have effused. Now, the word effuse, y'all, simply means to escape via a small hole. The hole could be a small opening at the top of the container. It could be like a pinhole when you simply open something like poke the side of a balloon. But simply put, it's saying which gas would move from that container into another area. Now, that's very different from diffuse. In diffusion, you're talking about it moving within the area itself. So when you talk about diffusion, it's like having something in one end of the room, a gas that you release in one end of the room, and it moving from that end to another end of the room. So again, if effusion is like moving from one container into another, diffusion is moving within the container itself. Alright, so with it in mind, the correct answer to this is actually B, that more hydrogen will have effused into the air. And the reason why that would be is if you're thinking about gases and moving, hydrogen and oxygen, as they move at different speeds. In other words, you think about their particles and you think hydrogen is very small, oxygen is a lot larger. So in comparison, which one do you think would be easier to move? One that's smaller or one that's larger? And the answer should be smaller, right? A particle that's smaller should more easily move through its area than a particle that's much larger. And that's why hydrogen generally expands more easily, but also it's why hydrogen as a gas, its particles, assuming that its energy is the same, its particles are going to move much more quickly. So more hydrogen will have effused into the air. Why? Because since hydrogen is so small, its particles will move faster. Now, with it in mind, again, reading what I had just said to you, diffusion and effusion, let's think about these words and understand how it is that particles move. So the way particles move is based on what we call their kinetic energy, right? And remember that we said that kinetic energy is generally just determining or dependent, if you will, on the temperature. The higher the temperature, the higher the kinetic energy. Lower temperature, the lower the kinetic energy, which means if two particles have the same kinetic energy, it's because they're at the same temperature. So two particles at the same temperature will have the same energy. Now remember, this is a formula that maybe you know, maybe you don't. If you had physical science ever, you definitely know this. But kinetic energy is simply, so Ke is simply 1/2. Now m is really just mass. V is velocity. Now to think about what velocity is, y'all, just remember that velocity is simply speed with direction. Now, why is direction important? Well, it's important because these particles are moving in specific directions, right? They're moving, again, where they're moving randomly, but they're moving in different ways. They're moving, some of them might be colliding with their container, some of them might be colliding with each other, but simply that's what velocity is. It's speed with direction. A word or a place where you might hear velocity a lot is when dealing with things like the weather and talking about how a storm travels. Like you think about some of the hurricanes that have happened in over this just last couple months, and when they talk about the hurricane, they generally talk about it in terms of velocity of the storm, which means not just how quickly it's moving, but the direction it's moving in, which is just as important, right? It's just as important that we think about where it's going as we think about how fast it's going. All right, so with it in mind, why, using this formula, why would it make sense that hydrogen would be moving a lot more quickly? Well, again, if we're assuming same kinetic energy, the same temperature, which they were in the same container, so they would have the same temperature, then as you decrease the mass, you would increase the velocity, or vice versa, right? So as you decrease the mass, if hydrogen has less mass, then it should move a whole lot more quickly. If oxygen has more mass, heavier, then it should move a whole lot more slowly. Now we put that into a calculation, and here's what we get. And it simply is this. These V's would be like saying the rate of diffusion, or the rate at which the gas moves. These M's are their molar masses. So the molar mass of gas V versus the molar mass of like gas A would give us ultimately the rate of diffusion of that gas. So simply the velocity of A over the velocity of B. And again, all that really means is the ratio of gas A's speed to gas B's speed. If you need to take a minute and jot that formula down, you should probably already have it, and we're going to use it in just a minute to solve a calculation. Alright, so let's just take an example. What if we were asked to do this? What if we were asked to determine the relative rate of diffusion for krypton and bromine? And let's just say, for the sake of, to keep it simple, let's just say we're going to call the first gas, gas A, and the second gas, gas B. Alright, so gas B and gas A, which means the relative rate is going to be the velocity of, this would be krypton's velocity over this would be bromine's. Now we don't have to be given the velocities, and we're not given them here, because remember, all we really need to know to be able to figure out the rate of diffusion, which is again what we called it on the previous slide, is their molar masses. So if we have the molar masses of krypton, which is gas A, and we have the molar mass of bromine, which is gas B, we could plug it in and figure out the rate of diffusion. And it would look something like this. So again, the rate of diffusion of krypton, so that's what we're seeing here, the rate of diffusion of krypton. Notice how we know it's the rate of diffusion of krypton, because we'll have krypton's velocity on top, bromine's on bottom, is equivalent to the square root of the molar mass of bromine over the molar mass of krypton. So we just plug it in, right? We plug in square root of molar mass of bromine. Now bromine's mass is really 79.9, but notice it's a diatomic molecule, right? So that's why there's two of them. So that's where this 159 comes into play. We've got 83.8 right here. Notice that. So, and that's krypton's molar mass. So we just simply plug it in, take the square root of that, and we get that the rate of diffusion is 1.381. Now, all this really means is it's greater than 1, right? So for every velocity of 1 for bromine, krypton travels at 1.381. So krypton travels more quickly than bromine. And it should make sense it does, right? We think about their particles. Again, if krypton has less mass, it should travel more quickly than bromine that has more mass. That's the idea, right? Let's take that idea and let's apply it. What if this was the question? A molecule of oxygen has an average speed of 12.3 meters per second, right? So we've got a velocity for oxygen at a given temperature and pressure. The question is, what is the average speed of hydrogen at the same condition, right? So this is the velocity of hydrogen. All right, so if we wanted to solve for that, probably thinking about gases, the easiest way to plug it in would be to set the velocity of hydrogen on top. Now think about it. The reason that is because it makes it a whole lot easier to manipulate our equation, right? This is what we're solving for. So we're going to make hydrogen gas A, and we're going to make oxygen gas B. All right, so with that in mind, what do? Well, again, we know their molar masses, right? So it's just a matter of plugging in their molar masses. If we plug in their molar masses, we plug in what we know, we can figure out what the velocity for H is. It would look something like this. Now notice where these numbers come from. 12.3 was given to us in the problem. Remember that these values are what? They're the molar mass. Again, why? Because they're diatomic, right? So oxygen's really 16, but there's 2 of them. Hydrogen's really 1.01, but again, there's 2 of them. So that's how we end up with those double masses. All right, now it's just a problem of manipulating our equation, right? Solving for our variable. So we do that. Again, this is what we had. If you need to jot that down, we do that, and this is what we get, right? That V sub H equals 12 or over 12.3 equals 3.98. Again, where'd that come from? That came from the square root of that 32 over that 2.02. So we get equals 3.98. Now we're just solving for velocity. So what do we get? We just manipulate our equation, right? Now we're getting rid of that 12.3 on bottom, multiply both sides by 12.3, and we get 49 for the velocity of hydrogen. Now, again, does that answer make sense? It should, because it's a lot greater than oxygen, right? Oxygen's velocity was 12, hydrogen's was 49, but why? Hydrogen's mass is smaller, oxygen's mass is much greater. So we've just quantitatively shown why that starter question about hydrogen and oxygen is, it's got to be B, right? If the mass for hydrogen is much smaller, it's going to move a lot more quickly, which means it's going to move out of that container and into its surroundings. All right, one more. An unknown gas diffuses 4 times faster than O2. Find its molar mass. All right, so the first gas is gas A. The second gas is gas B. Again, for just the sake of our understanding. And so let's just think about what we've got. All right, so again, we already know our formula, right? So velocity of A over velocity of B, square root of molar mass of B over molar mass of A, which means we'll plug this in, right? We don't know what the unknown gas is, but we're going to call that gas A. We don't know it. So we're going to call that gas A, because that's what we're going to solve for. Again, if we're trying to figure this out, we're going to want to know that by starting there, right? So we don't know that. We do know that we have the molar mass of oxygen. We don't know the molar mass of A. So let's just plug in what we know. This says that it travels 4 times faster than the other gas, which means this is really what we have, right? That 4 times is really just the rate of diffusion. right? By saying 4 times faster, we're really just saying the rate of diffusion. So that's why we could put that 4 there. Again, remember that this is really just the rate of diffusion. All right, so what do we have? We've got the square root of our molar mass of oxygen, which is 32, over our molar mass A, which we don't know. And now we see a problem, right? Notice this isn't a square root, so we're going to have to get rid of that square root. So what are we going to do? We're going to multiply both sides by, we're going to square both sides, not multiply both sides by 2, but we're going to square both sides to get rid of that square root sign. When we do that, we should get this, right? 16 equals 32 over our M sub A. So now, matter of manipulating our equation, and we get the molar mass of A is 2 grams per mole. Now, you might notice something, but more than likely that means that A is what? It's actually what we just talked about before, which is H2, right? If each mass of hydrogen is 1, then 2 of them would be 2. And that's the only gas that we have that would have a molar mass of 2. All right, let's go ahead and look at problem number 14 on your practice problem packet. I wanted to take a look at this problem because this problem is actually a little bit different from the problems that I just worked through with you, but it uses the same basic concept, and it's going to help us to really understand what's going on in terms of kinetic energy, as well as what really we use when determining the speed, because we've talked about, being given... We talk about being given things like velocity, but the question is, how do we actually calculate those velocities, or where did those velocities actually come from? So in order to understand that, I wanted to go back to the equation really quickly and remind you, remember, kinetic energy equals 1/2 mass times velocity squared, okay? And we also actually have another formula for kinetic energy, because remember that we said kinetic energy is equivalent to temperature. So we need some sort of formula that shows us that, and it's this, that kinetic energy equals 3/2 R times T. Now remember, R is really just that gas constant, T is temperature in Kelvin. But notice that we've got two different equations that give us the same thing, which means that we could technically set them up equal to each other, and it would look something like that. Now when we do that, what we actually end up getting is that if we wanted to measure velocity, that velocity would actually be the square root of 3RT over M, and M, generally speaking, is the molar mass, right? So when we say M, we're really just talking about the molar mass of that. Now, the reason I mention this is because you'll notice that in this problem it says what's the average velocity of helium at a certain temperature, right? We don't have the information we need to figure out like the molar mass of a gas or the rate of diffusion, because that's not what the question's asking. The question is asking what is the velocity based on solely what we have. We're not comparing two gases, we're only looking at one. But we have all the information we need, right? Think about it. We know that velocity equals 3RT over the molar mass. And here's what we know. We know T, which is temperature, is 25 degrees Celsius. But remember, we always want it in Kelvin, so we're going to add 273. And from that, we're going to end up getting what? 298 Kelvin. We also know R, but R is a little bit different because we're dealing with energy. Anytime we're dealing with energy, the R we're going to use is 8.31. That's joules per moles times Kelvin. Now the reason we use 8.31 when we're dealing with energy is because this R will now have joules in its value. Just to understand what joules is really just kilograms times meters squared over second squared. All right, so joules is really just kilograms times meters squared per second squared. And that's going to be important because this is actually the unit for energy. So anytime we deal with energy like speed and energy like energy with heat transfers, which is what we're doing in the next unit, anytime we're dealing with energy and gases, that will always be the unit that we use. So 8.31 joules per mole times Kelvin. All right, so we've got those. We've also got the molar mass, because remember, we're dealing with helium, so its molar mass is 4.00 grams per mole. Something to note, the unit in this R is kilograms, which is why anytime we're doing a calculation with this, our molar mass will be in kilograms, which is new, right? You've never had to do that before, but just note that anytime you would be doing a velocity and energy problem, that you're going to want your molar mass in kilograms. So we can do that by dividing by 1,000 grams, 1 kilogram. So really it's just 0.00400 kilograms. All right, so we've got that. So all right, so let's go ahead and plug in what we know. We've got 3 times our 8.31 times our temperature, which was 298 Kelvin, over, remember this is square root of, so over our molar mass, which remember we said was 0.004 kilograms. And solve, and we get 1362, that's meters per second. And the reason that's meters per second, you think about your unit, so joules is kilograms times meters squared per second squared. Our Kelvin cancels, right? Our kilograms per mole, so our moles cancel. Remember, this is joules is kilograms times meters squared per second squared, so our kilograms will end up canceling. We'll end up with meters squared per second squared, but it's a square root, right? So we take the square root of that, and that's where we get that meters per second. Now, with that in mind, based on sig figs, 2 sig figs would give us a value of 1,400 meters per second, and that would be it. We would be done. All right. Again, y'all, a few things about this problem. I'm not necessarily worried about you being able to derive the idea of where this formula came from. I hope you can see or at least get an idea of how I was able to come up with this velocity formula. Talking about, which is the average velocity, will sometimes be referred to as the root mean square velocity. Sometimes you'll see its unit or variable look something like this, U sub RMS, and that just means the root mean square velocity. And it's really just talking about the average velocity of a particle. Because particles move at all different speeds, we do this as like a distribution, so it's like a calculation that can be graphed, and based on that, that's how they actually come up with the average velocity of a particle of helium. But that's it, y'all. If you should have any questions about that problem, please don't hesitate to ask. And again, I will be here after school today, so you could ask me today. Otherwise, you can contact me between now and, again, practice quiz tomorrow and real quiz on Monday. With that in mind, I want to look at one more problem. All right. Here it is. Oxygen, O2, diffuses at a rate which is 2.23 times faster than a sample of reddish-brown gas. Determine the molar mass of the unknown gas. So let's think about a couple things we're given, right? So we're being asked to do rate of diffusion. So velocity of or unknown gas, right? Because we don't know it. That's what we're trying to figure out. I'm sorry. We don't know it. That's not what we're trying to figure out. But we do know the velocity of oxygen's, or the rate of diffusion of oxygen, is 2.23 times faster, which means, like saying velocity of oxygen over velocity of our unknown gas, we'll just put V sub gas, is 2.23, right? And we do know from what we just looked at that we could use the idea of molar mass in that to calculate the other molar mass, so it would look something like this. Molar mass of our gas on top over the molar mass of our oxygen. Now to remember why, remember that the formula is really just this, right? it's really just the opposite for molar mass than it is for speed. So that's what it looks like, right? It simply looks something like this, but I've actually got at least one number plugged in. But let's plug the other one in, right? So 2.23 equals the molar mass of our gas on top over our oxygen. Remember, it's O2, so 16 times 2, which is really just 32 grams. So we've got it set up, right? Now, square root, we want to get rid of that first. So the very first thing we're going to do is square both sides. Right, what we end up doing when we get that is 4.97 equals the molar mass of our gas over 32 grams. Isolate our variable by multiplying both sides by 32, and we get that molar mass is approximately 159 grams. Now, we think about that, and actually, it hopefully kind of makes sense, but that 159 molar mass, remember that a lot of the gases over on the right side of the periodic table, the gases that we look at as gases, several of them are diatomic, and one of them in particular that's diatomic is bromine. And remember that bromine has a mass of 79.90, but it's Br2, right? And Br2, so 79.90, we end up getting that it's approximately 159 grams. So it should make sense that this is probably bromine. But what makes even more sense is this reddish brown part to it. Bromine is actually just that. Bromine is a reddish brown gas. So just a way that we know that our answer has to be correct is just some basic information like that. And I didn't expect you to necessarily know that bromine was a reddish brown gas, but as we start to understand characteristics and we just a way that we can remember, characteristics. Chlorine, remember, is like a yellowish, greenish gas. Bromine is reddish brown. And those are just some ways that we might identify that, yeah, it makes sense that this has to be molar mass of 159 or bromine. And that's it, y'all. Look, you have just been shown number 14 and 15 from your Graham's Law packet. You've got one more problem to do, number 16. I'm not going to specifically show that one to you in class, but using the knowledge of kinetic energy, I think that one should be pretty simple for you to hopefully be able to figure out. And the reason is the fact that gases actually do have volume, right? And they do have masses, and they do attract each other. And there's various reasons why that can happen, but basically from this, what we can get is something that we refer to as the van der Waals equation. Now, in just a minute, I'm going to show you what the van der Waals equation looks like, but before I do that, I just wanted to make a note of a few things. So, one, like we said, gases generally are not ideal. Because of that, or what causes that to happen, one has to do with their volume. Now, I want you to think about it in terms of this. The larger a gas particle is, so you think about two gas particles interacting with each other, the larger a gas particle is, the more attractive forces between them. Now you think about why. You think about the larger the particle is, the more area there is in that particle, the more likely there is to be to be attracted or pulled in one direction or the other. Now you think about it kind of in terms of like even something like friction. Simply put, when two particles collide, there's a certain amount of force between them, right, as they hit each other. Well, when we talk about attraction, this attraction could be something as simple as when they're colliding, but it could also be because one of them maybe has a slight charge, like maybe the fact that the particle might be polar, which means it has an area that's positive and an area that's negative. And if that happens, particles that are negatively charged or positively charged could do what? They could pull or push on those other particles around them. And that pull or push would obviously slow those particles down, right? So that pull or push could slow or speed up particles. There could be a transfer of energy due to this, where we have energy that's actually lost in the form of something like friction or heat, right? So we're talking about simply that the larger the volume, the more likely they are to touch or interact, which means the more likely they are to slow each other down based on that. Now, another example or another way that we can change them would then be mass. And the mass of a gas, as it increases, well, the more slowly they move, right? And we just actually mentioned that as well, that the larger the mass, the slower the particle. So a more slowly moving gas would again do what? It would have more attractive forces between it, right? The more attraction, or the more likely it is to be pulled in one direction or the other. Now again, like I said, gases that are polar tend to be more attractive than non-polar gases. A perfect example would be something like O2 versus HCl. O2 is a non-polar gas. HCl is actually a liquid, but it can become a gas. HCl is a gas, or can be a gas. Why is it more likely to be a liquid? Well, because of those attractive forces holding those particles together. And as we get into the next couple units, we're going to start to see that it actually explains why all matter is the way it is. These attractive forces between the particles, based on their masses, based on the space they take up, will actually determine, whether they are slow enough to be solids versus maybe fast enough to be a liquid, or even more quickly moving, becoming a gas. Alright, so looking at the equation then looks something like this. Now, really this equation is just PV equals nRT, but it's a little bit more complicated, right? I want you to notice something about this equation, that all it really does is it takes into consideration, well, two things. It takes into consideration a change because of pressure and a change because of volume. So in other words, there's a deviation in the pressure of the gas because of how it's moving, and there's a deviation in the volume of a gas because of how it's moving. Now, you're not responsible for the calculation per se, but picture it like this. That deviation will actually increase the pressure of a gas, whereas that deviation will actually decrease possibly the volume of a gas. And so based on that, that's where we get that P and V equals nRT. Now, one more thing in trying to picture it, again, you're not responsible for solving a calculation with it, but you need to be able to look at, maybe a question that might ask you to use the idea of it to discuss what's going on. For example, let's just take that last question in your packet, question 17. So go ahead and turn to question 17 for me. And I want you to notice question 17. It says, in terms of the van der Waals equation, that equation we have up here, why is hydrogen chloride much less ideal than hydrogen gas? Now remember, we said that we're looking for two things. The idea of how it deviates from pressure, and the idea of how it deviates from volume. So what would we say? Well, we might say something like this, and you can write this down, you can think about it and write down in your own words, but simply put this: HCl has a larger mass, thus moves more slowly than H2. And HCl's particles take up more space, which will slow them down as well. Because of this larger mass, and because they take up more space, they will exert more attractive forces on their surroundings. These forces will increase the pressure while slowing down the particles in motion. So again, you could say all of those things, that they have larger mass, that they take up more space, that they have more attractive forces. All of those things do what? They cause the particles to move more slowly and to increase the pressure between them. And that would be it. And that would explain why it would be that it's much less ideal than hydrogen gas. If you should have any questions, please don't hesitate to ask. Otherwise, that's it, y'all. Again, this packet is due when you come into class on Monday to take your quiz. I've actually shown you, like 8 or 9 of these questions, which only leave you a few more if you haven't already done them to make sure are done. But just make sure you're getting this completed and that you have it ready to go, again, to turn in on Monday when you take your quiz. Practice quiz tomorrow. And again, if you have any questions, please don't hesitate to stop by and see me after school. Hope you have a great day.